Hello everybody, let's start lecture 41 and the course is on phase diagrams in single component and binary systems, and today's topic will be how to calculate isomorphous phase diagrams. In fact, what we have seen, the isomorphous phase diagrams looks like a kind of I-shaped feature where you have complete liquid solution over the entire composition range in a binary system, as well as complete solute solution range over the entire composition range. If we go beyond liquidus and below solidus, we have solid solution, and beyond liquidus we have liquid solution. But in between that I, any composition we take, that composition will be broken into two phases. One is solid solution, another one is liquid solution of two specific compositions, and those two compositions will be at equilibrium at a particular temperature. And whenever we draw isomorphous phase diagram, the pressure is kept constant. Here we are keeping the pressure at 1 atmosphere. So, we will continue the discussion, though we have drawn that isomorphous phase diagram from schematic representation of free energy composition diagram of solid and liquid solutions in AB system, and that too with an ideal solution consideration. And then we have just checked the equilibrium phases that can appear at a particular temperature, keeping the pressure constant at 1 atmosphere. So, that part we have done. So, now we will be in the today's lecture, today's as well as another lecture we will take, we will try to find out equations. By solving those equations with basic thermodynamic data, we can get isomorphous phase diagram for a binary system. So, we will try to show today that part. Now, if we try to look at what we have done till now, it is basically we have drawn isomorphous phase diagram. In a binary system A and B, where A and B are two metals, and if I try to see the melting point Tm, the melting point of B is greater than Tma, which is the melting point of A, and Xa and Xb are basically mole fraction of A and B. In fact, if we take only one mole of solution, then they would also become the number of moles in the system. So, that leads to 1 mole of solution. Temperature and pressure are constant, this is 1 atmosphere, and temperature. So, what we are doing, we are actually keeping the temperature constant and then trying to see the equilibrium between solid and liquid solutions at different temperatures. So, this is also fixed for a particular equilibrium consideration. So, that is what that is also we can say fixed. Now, of course, this is ideal solution, and solution would be a random mixture of A and B, and we have seen the diagram on a temperature composition plot. This is temperature and this is Xb. This side is pure B, which is Xa equal to 1, this side is pure A equal to 1, two extreme sides, and we have seen the diagram looks like this. So, where this is liquid, this is solid, and this is solidus, and this one is liquidus. We have seen this diagram. At the same time, we could see that this is Tma, this is Tmb, and if we take any composition to start with, let us say I take this composition, let us say this composition is X0, So, that time at this temperature, let us say this is T1, where at T1 we will if we start from a very high temperature, starting from complete liquid solution, at T1 the first solid solution of composition. So, this is the composition, let us say X S, or we can say X B with reference to B of solid, X B solid would appear, and rest of the thing would be liquid. We have seen that before. Okay, why it becomes completely liquid. Okay. Most of them are liquid, only a very tiny bit of first solid solution would appear. This is, we are starting from complete liquid solution. So, that means we are cooling. Okay. Now, similarly, if I see this temperature, let us say this is T2, at T2 if I start from at this location and if we keep increasing the temperature, the first liquid solution of composition, if this is the composition of liquid. So, let us say X B liquid would appear, and we are starting from a lower temperature where everything is complete solid solution. So, now if you see below this temperature everything would be solid solution, beyond this temperature everything would be liquid solution, but between this point and this point there will be mixture of solid and liquid solution, but the composition will keep changing. Okay. So, at T2 the composition of solid would be X0 and liquid would be X B liquid, and T1 composition of liquid would be X0, but the solid solution composition would be XBS. Okay. Now, in between, let us say I am choosing one temperature in between. So, if I choose a temperature here, let us say this temperature is T prime, at T prime we will get two different phases. One would be X B prime, this particular thing would be X B prime of liquid, and this one would be X B prime of solid. Okay. So, these two phases it will break into, fine, and we will get. So, at T prime solid would have solid solution would have composition X B prime solid, and liquid solution would have composition X B prime liquid. Okay. These two phases would be there. Now, here we can also calculate what would be the fraction of phases, okay, and that too weight fraction. So, weight fraction solid solution would be given by X 0 minus X B prime liquid divided by X B prime solid minus X B prime liquid. Okay. This would be my solid solution weight fraction, and weight fraction of liquid solution would be equal to X B prime solid minus X 0 divided by X B prime solid minus X B prime liquid. So, these two cases, for two weight fractions can be obtained from lever rule. So, this is called lever rule, and that is obtained from mass balance. Okay. We have done that also. These many information we can definitely get out of an isomorphous phase diagram, and that too we have drawn with respect to free energy composition plot and checked the common tangent as well as the free energy hierarchy, and see which phase would be stable at different temperatures, keeping the pressure constant at 1 atmosphere. Now, we will try to calculate it. In order to calculate, we have to check 3 basic plots. Okay. So, we will do it. This is the phase diagram. Let me just draw it. So, now we will try to calculate. This is the phase diagram. This is TMB, this is TMA, temperature, XB composition, XB equal to 1, XA equal to 1, fine. And for pure metals, we have seen G versus T. So, since melting point of B is greater than melting point of A, so schematically we are seeing like this. This one is, let us say, TMB. So, then definitely this would be B of solid, this will be G naught B liquid, and for solid, for A we will get a diagram like this. So, where this is nothing but TMA, and here this is G naught A solid and this is G naught A liquid. Okay. This diagram will be referred to. Why? Because we have to, as we have seen that we have to assign a reference 0 value to the most stable phase at a particular temperature. Whatever temperature we consider over this G versus T plot, the stable phase will be taken as 0 for the free energy of the pure component. Okay. So, that we have already learnt how to do it. And what we will be doing? We will be trying to evolve those equations for finding free energy, finding isomorphous phase diagram. So, we will be doing all the analysis at temperature, let us say T. Okay. This is the temperature we will be doing the analysis. And at this temperature, if we do analysis, and now that we just keep changing the temperature in those formula, then we can get 2 compositions at equilibrium. One composition would be solid composition, which is XB of S, and another composition would be XB liquid. These 2 composition at different temperatures, if we keep finding out, and then we keep plotting those composition. So, we will be plotting those composition. These are, let us say, liquid composition at different temperatures. So, this and this. So, correspondingly, we will get solid composition as these points, and one solid composition would appear here, another would be here. So, like that, all those liquid compositions will be connecting, and then the solid compositions will be connecting, and all those compositions will be in equilibrium. So, then we will definitely get this isomorphous phase diagram. Now, if I do the free energy composition diagram at T, so the diagram would look like this is X A equal to 1, this is X B equal to 1, 2 extreme composition, X B would be varying this way, and these are the 2 0 points, and we are trying to do it at temperature T. Okay. So, now at temperature T, if we try to find out 0 value, the reference 0 value for free energy of pure A or B, now at temperature 2 is actually lying in between 2 extreme temperatures, 2 melting points. So, this is the temperature we are talking about, this is the T. Okay. So, at that temperature, as from this particular free energy temperature diagram for pure metals, we can see that G A naught liquid should be assigned, 0 should be assigned there, G naught B solid should be 0. So, that is the reference point. Now, accordingly, the other free energies for pure metals will be placed. Now, this point would definitely G B naught solid, and this point would be G A naught Ga naught liquid. Now, if you see a G versus T plot, then definitely I see that this would be liquid, and for A, this point would be Ga naught solid. Fine. So this would be 0, this will be 0. Okay. Now we see that this is basically nothing but G1 for solid, and we have to find, that is G1 basically the before mixing, what is the free energy, total free energy, and this another one is, this is G1 liquid. Okay. And we know that G2 solid slash liquid would be equal to G1 solid slash liquid plus delta G mix solid slash liquid. Okay. So if we take solid solution, everything should be solid, and if we take liquid solution, everything would be liquid. So even the composition, we have to assign the liquid composition. Now G2 is the free energy of the solution, and G1 is the free energy before mixing, okay, unmixed condition. And delta G mix, which is nothing but, if we try to see this, RT XA ln XA plus XB ln XB. Okay. So that is the formula what we have got for delta G mix, and there this will be same for same contribution it will provide at a particular temperature to G2, okay, but G1 would be different. Now this particular thing, let us say if I try to do for solid, so everything would be for solid, and if we do it for, so this would be also solid, this would be also for solid, this would be also for solid. Now if we try to do it for liquid, this will be all for liquid. So nothing can be mixed when you write this equation. If we write for solid solution, everything, whether starting from composition to G1 to G2, you should put S for solid, and for liquid everything should be liquid. Okay. So that you must consider that, otherwise there will be problem in finding out the equations. So if we do it for solid G2, so solid G2 would be, this is solid G2, and liquid G2 would be, this is G2 solid, and the liquid G2 would be, this is would be G2 liquid. Okay. Because G2 liquid will corresponding to G1 liquid and G2 solid will correspond to G1 solid. And in order to find out equilibrium between solid and liquid phase and which two compositions will be under equilibrium, so we have to draw a tangent. So the tangent would be passing through, that is the common tangent, and we know why we have to draw the common tangent. This is XB of liquid, this is XB of solid. Okay. These two compositions. And let me just mark some of the points. Let me mark it like this. Let us say this point is A, this point is B, this is C, this is D, this is E, and this is F. Okay. These are the points we are considering, and here we see that GB bar of solid should be equal to GB bar for liquid, that is the condition of equilibrium. The molar partial gives free energy for a component in both solid and liquid should be equal, that is the condition of equilibrium, and at this point GA bar solid should be equal to GA bar liquid. So now we have to find equations for GA bar solid as well as liquid and GB bar for solid as well as liquid. So let me just write down those equations. We can do it like this. This is GA bar solid slash liquid should be equal to G2 solid slash liquid plus XB solid slash liquid GXA solid slash liquid. Okay. Similarly, we can get GB bar solid slash liquid should be equal to G2 solid slash liquid plus XA solid slash liquid G2 solid plus liquid now XB solid slash liquid. Okay. So now if we want to find out GA bar for solid, everything you just omit liquid part and then everything you only keep the solid, which is the superscript. That solid you just keep it, and then things will all be placed accordingly. Fine. So these formulas, 4 formulas will be using, one for solid, another for liquid, for A, and similarly it will be for B. Now let us also put some, let us get the G1L as well as G1S equation at any composition. Okay. So for if we try to find out for solid before mixing, that is the total. So if we try to find out total free energy G1 solid at any composition, if we try to find out, and that composition will take it as per XA. Okay. So if we try to find that, okay. Now we see that these two are 90 degree, this angle as well as this angle are 90 degree. Okay. So now first, in order to find the equation for G1 solid, that is unmixed G1 at any composition, we have to deal with this particular triangle, which is this, okay, where this point is XB equal to 1, this point is XA equal to 1, and XA is varying this way. Okay. So this way, and so XB equal to 1, so that means XA equal to 0, and this particular thing would be A, C and D. This is 90 degree. Let us say there are two angles, one angle is theta. So this is, let us say, theta solid, and let us say the other one is theta liquid. Okay. So now if this is G A naught for solid and this is G A naught for liquid. All the markings are done. Now for this, let us say delta G naught A, let us say M, let me just find out the free energy difference for melting of pure A would be G A naught liquid minus G A naught solid. Since we are taking melting, so that means the final phase is liquid. So this can be termed as delta G naught M for melting for A. So now we see that liquid, this is assigned as 0 as per this particular free energy composition diagram. So now if I try to find out AD, so that would be minus of GA naught liquid minus GA naught solid should be equal to minus delta G naught m A. Okay. Now, if I G1 S is nothing but G1 S, so that is nothing but the slope for CD line. Okay. So that is nothing but theta solid, that tan theta solid, that is the slope of CD line. So now we can find out, let us say any composition, I take this composition, let us say this is the composition I am taking. So at this composition, if I try to find out G1 S, and let us say this point is G and this is H. So I can write, considering that this is right angle, this is 90 degree. So now I can write AD, that slope is AD by CA should be equal to GH divided by CG. I can write this. Okay. So both are considering the slope for both are considering tan theta S. So which is nothing but tan theta S. Okay. So then AD is nothing but minus delta G naught M A divided by CA is nothing but XA equal to 1, should be equal to, this is G1S divided by CG is nothing but XA. So let us say this particular point is XA, that is the arbitrary composition what we have chosen between two extreme positions, XA equal to 0 to XA equal to 1, and all the compositions are with reference to A, remember. Okay. So then from this we can get G1S should be equal to minus XA, and remember this is for solid delta G naught M A. Okay. So this is the equation what we are getting. Fine. That is the free energy at any composition XA, and remember we are doing it for solid. Now we can get G2 for solid, which is nothing but G1 solid plus delta G mix solid. Okay. So then I can write minus XA solid delta G naught M A plus RT XA solid ln XA solid plus XB solid ln XB solid. So I do get an equation for G2 solid at any composition with respect to A from XA equal to 0 to XA equal to 1. So this composition, let us say this equation is 1. Okay. Similarly, if I try to do it for let us say I want to do it for same thing for of course, here we have also found out the equation for this equation for solid solution, which is G2 solid. Now for liquid unmixed before mixing, and if I try to find out total free energy G1 liquid at any composition, and here I will be doing with respect to B, and this would be liquid. So if I try to do that, I have to, if I go back to this equation, to this particular graph, which is G versus composition plot. So this is G and this is the composition. If I take ABC triangle, So, if I take ABC triangle, let me do that. This is ABC triangle, and this point is XB we will be doing with respect to B, and this point is XB equal to 0, and we are doing it for XB composition we are varying, and this point is GB not liquid, and this is GB not solid, and this is A, B and C. This is 90 degree and this is theta liquid. Okay. So, I can if I try to find out let us say this value is Mn. Okay. So, this is let us say G1 liquid, and this particular line corresponds to G1 liquid line. So, if I try to do at any composition this G1L, if I try to find out, so then I have to see tan theta liquid should be equal to CB divided by AC should be equal to Mn divided by Am. I can do that. So, now if I try to look at delta GMB, that means melting free energy change for B should be equal to G naught BL minus G naught B solid. So, then this would give me CB should be equal to delta GMB, since delta GM naught L is having higher value than delta GB solid at temperature T. So, this that means CV value, okay, divided by, now AC is nothing but XB equal to 1 should be equal to Mn is G1L divided by XB. So, let us say this composition is XB. So, this gives me G1L should be equal to XB, and of course, this is for liquids composition, liquid delta G M B naught. So, here one must put that naught because this is for standard conditions. Okay. So, we got equation for G1L, that is unmixed condition at any composition between XB equal to 0 to XB equal to 1. So, now we can definitely find out for equation for liquid solution, which is G2 liquid should be G2 liquid should be equal to G1 liquid plus delta G mix liquid. So, I can take G1 as XB liquid delta G naught M B plus RT XA liquid ln XA liquid plus XB liquid ln XB liquid. Okay, fine. So, now we got equation for G2L, and this can be termed as 2. Now, once we know that the equation for liquid solution and solid solution with respect to composition as well as free energy change for metal A as well as metal B, then our entire effort should be how to get these 4 conditions, and those 4 conditions can be met at E and F. So, these are the 2 points we will be trying to find out those 4 conditions for finding molar partial Gibbs free energy for A and B in solid and liquid solution, and then we will equate them. So, actually we will be using this one as well as this one for finding out 2 specific composition XBL as well as XBS, and then we can solve XBS as well as XBL. And for that, what we will be needing, this is interesting now, what we will be needing? We will be needing this quantity this quantity will be needed, and another quantity is this one will be needing. Okay. And remember, these two quantities can be obtained from a simple formula. That formula is like this: delta G m B should be equal to delta H naught m B, which is the standard enthalpy change for melting of B into T m B minus T divided by T m B. And remember, if you recall, we have actually found out this equation in earlier lectures. And similarly, we will get for this one, which will be, this is delta G naught m A would be equal to delta H naught m A T m into T m A minus T divided by T m A. Okay. So, that way we can find out. Now, compositions, now what data will be needing? We will be needing this quantity, and this quantity. So, that means 4 data will be needing. So, what are those 4 important data will be needed for finding out, for calculation of isomorphous phase diagram? These 4 data will be needing. These 4 data will be needing to solve those equations. We will see that. Okay. Now, these 4 data can be easily obtained by doing one particular experiment. We call it differential scanning calorimetry. So, we can find it from DSC experiment. This is a fairly easy experiment, and those are experimentally found out data for POR A and POR B, and those data will be used. Okay. So, it is a simple thermodynamic data can lead us to find out isomorphous phase diagram. Of course, now we will be solving for those partial quantities at E and F, those 2 points. Okay. So, now we will stop now, we will extend our discussion in our next lecture, and there we will be solving for partial molar Gibbs free energies of A and B in solid and liquid solutions, and then we will equate them as per equilibrium condition, and we find out equations to solve for those 2 compositions for solid solution and liquid solutions at a particular temperature. So, let me stop here. Thank you very much.